So, in the last class we try to understand what is the meaning of stereographic projection. So, let me remind you once again that stereographic projection is something, this is the case. So, if I want to find a point here, say this point is P, then for each point I should have a unique point here, and we say that there is a relationship between this point. Say if this is y and this is xi2 xi3, then we calculate something that this divided by this is these things divided by these things is equal to these things divided by these things. In different way you can do that. I mean, this is not a unique way to do the relationship, but the point is that you can find y as a function of xi1 and xi2, and when you do that, that means for each xi1 and xi2 or xi3, here xi2 and xi3, because I am not taking x. So, for each value you will have a unique value of y. So, if y tends to infinity, this point goes to here in the north pole. You can do that. I mean, this is not a very hard thing to do. Today we will start something important, as I mentioned in the last class, which is complex functions. So, real function we know. What is the real function? So, let me go back to this function analysis and all these things. So, I have function is something which is rule. We have a set of point here which I call the set of point x. I apply the rule, and as a result I am getting a set of point, and the rule I call fx, and this is y. So, y is fx is the rule, and for each point I should have another point here. This is called the domain, and this is called the range. So, I will take one point from domain, I will apply the relationship or the rule over that, and I am getting another point in another domain. So, which is called codomain or range. So, example is, say y is equal to x square. I take one x value here, I squared that, and I will get another point here. I take another x squared that I am getting, and if I do that, then I will have a relationship between this. So, I will have y, I will have x. For every x I can plot y here. This is the rule. So, if I plot, I will have a parabola. So, no problem with that. If I have a different kind of function, I will have different. So, if I have y e to the power x, I should have a different kind of function, and if I plot, it will be something like this, and so on. So, the point is that I can always plot, in real case I can always plot one variable with respect to other. But what happened in case of complex function? So, let us first define what is the meaning of complex function. So, complex function is the same thing that I have a set of complex point, say z. This is a set of complex point. In the complex plane I have a set of point in a region, as I mentioned in the previous class. I apply a rule of that point. This is the point in the complex plane, set of complex. So, that means this is called z plane, this is x and this is y. So, in the z plane I have a distribution of points, and over that particular point I apply the rule exactly the way I apply, and as a result I am getting here something. Now, the question is, whatever I am getting is also essentially be a complex number. So I called it as W, and I can also put these things here, but now my plane is changed. This complex plane, if I write this complex plane as jet plane, then this complex plane I shouldn't write the jet plane, I should write is as W plane. In the W plane I will have a distribution of point, because of the fact I am applying one rule over that and different points are start generating, but since these points are again complex points, so I should have a real and imaginary axis here like previous, but I shouldn't write it as x and y, rather I should write it as u and v. So in sum I will have z equal to x plus iy, this is my variable. I apply my function fz over that, this is the rule I am applying over that. As a result I am getting something w which is u plus iv, which is again a complex function, and this complex quantity, this complex quantity I should write in this way. Now if you note that u and v should be function of x and y both, so it is better to write u xy plus I v xy. There are different kind of function you can imagine. So this is the first I need to understand what is the rule here, or what is the meaning of complex function. It is exactly like the real function. In the real function I have a real variable and I apply some kind of rule over these real points or real variables, and as a result I am getting something which is real, and this real thing is governed by something which is called fx. But here I am doing the same thing, the logic is same, but instead of having x I should have z as my variable, which contains two variable x and y. Now when I apply these things through a rule fz, I am getting a new thing which I call w, but interestingly this w is also complex, so I should write u plus iv, where u should be a function of xy and v should be a function of xy as well. Now let me give you some straightforward example, then things will be clear. So after having a very basic idea about how the complex functions working, so say fx fz is say z square, this, so my rule is given. So what is my z? X plus iy, this is my z. What is my z square? By the way, z square is nothing but w. What is z square? Z square is x plus iy square, which is x square minus y square plus 2i xy, that quantity, and that quantity is nothing but u function of xy plus I v function of xy, because my w is u plus iv, so u xy should be correspond. So when both the things are equal, then I can readily write u of xy is x square minus y square, and v of xy is 2 of xy. This is the relation. Now the problem is in the complex plane, the problem is you can't draw anything, because two variables are associated with z. For these two variable again you have u and v. U and v is associated also two variable. So in the real case there was one variable that is associated with that, and you can plot this one variable to another variable. Here you have two variable associated with z. So when z is changing, essentially two variables are changing. When two variables are changing, then it is difficult to in 2D it is not possible to draw v and u simultaneously. What you can do, that you can fix one value and then plot and then find out the relation. I will do one simple problem, but before doing that let us try to find out few other functional form also. So this is this. So what is function of say z minus real part of z? This is also a function. So this function, if I write in the xy form, so w is x plus iy, and real part of x means it is minus of x. Real part of z means it is real part only. So this. So if I write, it is just iy. So iy, so that means u of xy here 0, v of xy is y. There are different kind of function you can consider. For example, mod of z square minus real, say imaginary part of z plus I. This is also a function. Mod of z square means x square plus y square minus imaginary part of this quantity. What is the imaginary part of this quantity? What is the imaginary part of this quantity? So z plus I is equal to x plus iy plus I. So x plus I y plus 1. So real part is this, and when I say the imaginary part, that means this quantity. So this quantity is nothing but y plus 1. So entire function now become a real function. The way I define this, it's maybe a real. It is not necessary that function of z is always gives you a real or always gives you a imaginary. It may be complex, and real thing is nothing but a special case of complex function, complex quantity. So that means here I should write u xy is x square plus y square minus y plus 1, and v xy is 0 because there is no imaginary part associated with this. Okay, so after having these things, let us go back to that problem to how to define a function. So let us say this is my function fz is equal to z square. Now since we are not able to, so it was I do that. So my u xy was x square minus y square, and v xy was 2xy. What I am trying to do, that I try to find out for different z how this u and v is related. So since it is directly, it is not possible to draw the variation, what we can do is called the mapping. It is called the complex mapping. So what I will do in this mapping procedure, what I will do, that my z variable is changing. So in z plane I will vary my point real and imaginary, which is x and y. This is my z plane, and try to find out that if the z point is varying here, how in the w plane things are changing. So here this is u and this is v and this is w plane, and related with the function which is defined here, fz is equal to z square. Now in order to do that, as I mentioned, I need to change my variable to a single variable. So that is why I say x is 1. So I fix my x, and y can vary. So that means in the z plane the variation of z with the limit, with the restriction y equal to 1 should be this line. So my z is varying over this line in my z plane. So my z point is varying over this line because y equal to x equal to 1 is my point, x equal to 1 is the restriction, and x equal to 1 is nothing but this point, this line, and over this line my z is changing. So that means whatever the y value I can think of, so my z is essentially 1 plus iy. So there is no restriction of y, so y can change like this. If my z is changing in this way, what will be the form here in u and v? That is the question. So the problem is z is changing like this way. I want to find out how it will look like here in w plane. It is called a mapping. So I want to map this particular variation of z with the restriction x equal to 1, so that I can do that. So here we have a relation, so I can just put this x equal to 1 here and try to find out what is the relationship between u and v. That's all. That is the recipe of doing these things. So I have x equal to 1 in my hand here. What I will do, that I will put this condition here. When I put this condition here, I will have a relationship between u and v, and then I put this relationship. So u will be, if I put x equal to 1 minus y square, and my v is, if I put, so it will be 2 of y. So I should have a relationship between u and v, and the relationship is u is equal to 1 minus y square. If I say, it will be v square by 4. This is the relationship between u and v. After having a relationship between x and after putting a value x equal to 1, I have a unique relationship between these two. If I now plot this point, these things, how it look like, that is the answer. So it seems that when v is equal to 0, when u is equal to 0, v is how much? V is v square by 4 equal to 1, v square is equal to 4, so that means v is equal to plus minus 2. So at this point the value of v is here and here, which is 2 and 2. This is 0.2, this is minus 2. Right? And then when v is equal to 0, then u is equal to 1. So somewhere here, this is 1, and it seems to be a parabola. So simply it will be something like this. It will be something like this. So this is the mapping of this particular straight line, for which I should have a restriction x is equal to 1. Now when I have a restriction x equal to 1, I should have a straight line for that. That means this is my variable. Now my z is not vary over the entire plane, rather it is varying just one single line, and when we have a one single line variation, then I can map this to the w plane and try to find out with this relation, when u and v are there, how u and v is related, and I find that the relation. So this is the one example of mapping. Okay, after having the relationship of mapping, so let us now try to find out something interesting, which I already mentioned actually, is the limit. I am not sure whether I will be able to complete this topic today, but let me first introduce what is the thing. So concept of limit. So limit is a well known concept in a real case. When you have, in the real case, say this is my real axis one point is x, and because of when I have limit, that means say limit x tends to x0 fx is say L. The meaning of this line is that x minus fx minus L will always be less than equal to some quantity delta if my x approaches to x0 in such a way. So, for every x which is following this relationship, that means x minus x0 is less than a small quantity delta. So, that means for that x, if I put this x here, then this value will be close to some other value L, with the fact that if I take a mod of these things, that should be less than delta. So, as if I go to closer and closer, this quantity f for every x which is following this epsilon, which following this relation, I should have additional relation between these two things, so that I will have a f minus L is something less than delta. So, this is the delta epsilon, the well known delta epsilon relationship between when we define the limit of that. So, we know these things for real case in our previous courses. It has been taught very rigorously. So, I am not going to be detail in that. So, I believe all of you are aware of this. Just this is a recap how the limit is defined. So, now I am going to do the same thing for complex. So, my complex case z is go to z0, f of z goes to some value say L. In this case also I should have a relationship that fz minus L should be less than delta when z minus z0 is less than some epsilon. So, I have, so z minus z0, you can understand that this is basically a circle in the neighborhood of z0. I will have a point here z, I am approaching to this point z0 with the condition that it should be less than these things. Here in w plane, when I put this function here, so I will have this in w plane. So, w plane also I have a point L here, and my fz or w is such that they will also follow the similar kind of things. So, something like this. So, I am approaching this point, z is approaching to z0 with the limitation that it should be less than some quantity epsilon. As a result of these things, in the another plane I should have this quantity which is also approaching to L with the limitation that this minus this mod of this minus this should be less than delta. Okay, this is one thing, but the important thing is approach. Let me draw that in a bigger way. So, this is my z0 point. When I am saying z tends to z0, so it can approach from this point to this point, it can approach this point to this point, it can approach this point to this point, it can approach this point to this point, and so on. There are infinite number of way to approach this point, as I mentioned in my earlier classes, that there are infinite number of way to approach. In real case, what happened? So, I want to find out the limit x tends to x0 fx is equal to, I want to find this limit. So, what is the value of limit? First, what we choose, left hand left hand limit, that means when I approach from, this is my point x0, when I am approaching from this side to this side, it is there. First I check. Second thing, left hand limit exist, checked. Right hand limit exist, check. If these two limits are same, so right hand limit is equal to left hand limit is equal to the value of function at that point. If it is true, then we can say that the limit is there, so limit exists. But here, since the approach is not left hand and right hand all the directions, so we are in some trouble. So we are not directly, we can not say whether it is approaching to this limit or not, whether the limit is exist or not. So let us take a very straightforward simple example before the end of this class. Next class again we will start from this concept. So let us try to find out limit z tends to 0 mod of z square divided by z square, mod of z square divided by real part of z square, say something like this. I try to find out the limit at z equal to 0. Just give one example, then I will show more things. So what is the case here? Z mod of z square is how much? X square plus y square. Real part of z square, what is z square? Mind it, z is x plus iy. What is z square? Z square is x square minus y square plus 2i xy. When I say real of z square, it is x square minus y square, this quantity. So if I put here, eventually what I am saying that z tends to 0, which essentially means x tends to 0 and y tends to 0. This quantity is x square plus y square. I just put everything in terms of x and y, and this quantity real of x square is x square minus y square. I have this. So this is my condition, this is my limit I need to find out. So limit z tends to 0 is essentially means this, right? So now I will do one by one and check. So before that, let me draw one thing here. This is my 0 point. When I say x tends to 0, y tends to 0, I will have several options in my hand. One option is this x is equal to 0 and y approaches to 0. I can go with this line. I put x equal to 0 directly, so that my calculation is simpler, and I approach y tends to 0. This is my one path. Say this is one approach, approach 1. Another approach you can readily understand, maybe this. I can approach from this side. This side, what is the condition? Y is equal to 0 and x approaches to 0. This is approach 2, and I can put any arbitrary direction. I can go to 0 from any arbitrary direction. So say I can approach to this direction, this direction, y, where y and x are having a relationship. So that means y is equal to mx, that is a relationship. So that means y is approaching to 0 and x is approaching to 0, both are approaching to 0. In this case 3, I put it as a special case, case 3, both are approaching to 0, but they are maintaining a relationship y equal to mx. M is a slope. So that means through this straight line where m is a slope, they are approaching to this point. So there are 3 different cases where you can apply. So because I need to check whether the limit exists or not, in order to check you need to ensure that whatever the direction you want, whatever the direction from which you can go approaches to 0, you will be able to reach this point. So if I do, then you can readily understand for case 1, what happened, I put x equal to 0, y tends to 0, that means x equal to 0, y tends to 0 gives you what value, limit y tends to 0, I will have y square minus y square will cancel out, I will have a limit minus 1. So I can have in fact a value of the limit. Case 2, in case 2 y is 0, x is tends to 0. So if I put y is 0, then limit x tends to 0, here y is 0, here x is 0, here y is 0. So y is 0 means this is going to vanish, I will have x square by x square, which is plus 1. Readily I find that in 2 cases, in first case the limit gives me minus 1, in the second case the limit gives me plus 1, that means they are not equal. So that means the limit does not exist. From here I can conclude, but interestingly in case 3 you will find something again. So here both limit x tends to 0, y tends to 0, and if I put that there, then what happened, the relationship if I put, then if I put y is equal to mx square, then it will be x square plus 1 plus m square, and in the downstairs it will be x square 1 minus m square. So x square will cancel out, I will have a value of the limit which depends on m. That means it depends, the limit entirely depends on in which direction you are approaching to the point 0. That means this limit does not exist. The answer is the limit does not exist. So here I like to stop, because in the next part we will go to more detail about the limit continuity and the derivative, which is most important part here. So before going to the derivative of complex function, what is the derivative, meaning of derivative of the complex function, we need to know what is the meaning of the limit of a complex function. And we find that here the major difference between the real case and imaginary case, real case and complex case, is that in the complex case the approach of a particular point can be in from any direction, and since it is in any direction it is difficult to find out the limit, but there are few things through which you can find out whether the limit is exist or not. In the next class again we will start from this concept of limit and find out, do some kind of problems related to limit, find whether the limit is exist or not and all these things, and then go to something called the derivative of a complex function, which is much more important here, and then try to find out something quite important in the complex analysis, which is called the analytic function. What is the definition of analytic function, what is the meaning of analytic function, maybe in the next class we try to cover this. With this let us stop the class here. So see you in the next class, and thanks for your attention.